Now we're going to get into when the antibody sees the antigen for the first time. This is what we call antibody-mediated immunity or humoral immunity because it's of the body humors, of the body fluids. This antibody-mediated immunity is going to be governed by B cells. And B cells are going to respond to antigens and they're going to make antibodies. So first what happens is a primary response. This is the first time that our immune system sees the antigen. Now, this could be through natural means, so getting the flu, or it could be through means of artificially introduced, so getting the flu vaccine. This is the first time that our immune system is seeing this antigen and recognizing it as foreign. So these B cells are going to respond to the antigen and they're going to start to make a lot of these antibodies. So the two types of B cells that we talk about are plasma cells. Plasma cells will rapid fire off a bunch of antibodies. And some of those B cells will differentiate into memory B cells. And those memory B cells are going to help us with our long-term immunity. So they can circulate around for weeks, months, even years, so that if that antigen presents itself again, our immune system is going to be able to recognize it. So let's imagine our primary response is getting the flu vaccine in the fall. So that antigen is introduced to our immune system, and our immune system has a primary response. So B cells are going to recognize it. They're going to make a whole bunch of antibodies to fight that antigen. And some of those memory B cells are going to be produced. They're going to help us with the secondary response. So the secondary has to do with our long-term immunity. And this means that our immune system has memory. They often call this the anamnestic response because it doesn't forget because of those memory B cells. Now, the secondary response is going to be bigger and faster, and we'll talk a little bit about why that is. So let's imagine our primary response was getting that flu vaccine. Our secondary response is when we are actually exposed to the flu. So we spent the weekend with somebody with the flu, and that antigen was introduced into our system. So our body is recognizing that antigen as being foreign because of those memory B cells that remember that antigen from our vaccination. Because we have the binding of antigen and antibody, plus we have that danger signal that, okay, something is wrong. We've got a pathogen that's coming in here. We need to do something. We're going to turn on those B cells. They're going to clone themselves like crazy, and we're going to get a bigger response. We're going to have more antibodies, and because of those memory B cells, it's going to be much faster as well. So that secondary response is a bigger, faster response. Now, hopefully it's a big enough response so that we don't get sick, or maybe not as sick if we hadn't had that flu vaccination before, to at least manage it on our own and not end up in the hospital. So the antibody-mediated immunity basically has these two steps: the primary response, and then that secondary, never forgetting response, which is going to be bigger and faster. And if our body takes it seriously, hopes to keep us healthy. So what are the functions of these B cells? Well, first off, they make antibodies. And I mentioned those plasma cells. Plasma cells can rapid fire off these antibodies, so about 2,000 per second. And remember, these antibodies are going to recognize antigens, and they are going to bind to those specific epitopes of the antigen. So if you remember, I said that an antigen can actually have several epitopes, which means that many antibodies can actually bind to it. I used to think that it was one antigen, one antibody, but an antigen can actually have many epitopes, and that means that we would need many antibodies to actually bind to them. The other thing that B cells do is that they can actually present antigens to T cells. And usually once B cells find an antigen and bind to it, they can actually display that antigen on their cell surface. This is almost like a storefront window in how they set up displays. So if you're going window shopping and you're looking in the displays, you're looking to see if maybe that store has something that you would like to buy. It's the same type of thing with the B cells. They're kind of saying, look at what I found. And so they kind of wait and pause a little bit before they start cloning themselves like crazy until they present that antigen to a T cell. Now, I talked about our T cells as being kind of like the intermediaries. Without a healthy T cell population, we basically have no immunity. So the B cells are waiting for these T cells to inspect them. And once a T cell recognizes that antigen as being foreign, it says, yep, that thing is bad. Okay, start cloning yourself like crazy. And T cells are also going to come into play as well. So B cells make antibodies, and they're also going to activate T cells and wait for that inspection from T cells. So let's talk about the different types of antibodies. So a term that you often hear associated with antibodies is immunoglobulins. Now, an immunologist would definitely differentiate between an antibody and immunoglobulin. I tend to use those interchangeably, just so that you know some of the differences. Immunoglobulins are bound to B cells, where antibodies will actually float. And I showed you another picture of an antibody, an immunoglobulin, and they're a Y-shaped protein. We talked about that heterogeneity of those variable regions that allow them to recognize antigens that maybe we haven't seen before. So they're going to be defined by the constant regions. And there are different types of antibodies or immunoglobulins. So I often think of the acronym GAMED. So there's IgG, IgA, IgM, IgE, and IgD. It's the variable regions that are going to determine the binding to the antigen. And remember, because of that gene expression and that heterogeneity, we can get many, many different variable regions that will bind to different antigens, some that we've never even seen on this planet before. Who knows what's coming at us in the future? So this is a blown up picture of an antibody right here, and you can see where it is that Y-shaped protein. We've got the constant regions that define what it is, and then the variable regions which are going to bind to those epitopes. So we'll talk about the different classes of immunoglobulins. And again, I always think of the acronym GAMED. So the first one is IgG, and this is the main immunoglobulin which is found in blood. This is going to recruit phagocytes, and it's also going to activate complement, and it can even cross the placenta, and it can be found in breast milk. IgG is one of the main ones that we see and that we also talk about. IgA, we can find small amounts in blood, but it's actually going to be in large amounts in secretions and places where we have mucous membranes. So remember, mucous membranes are going to be the easy access for pathogens to get in our body. So this is where IgA is going to be, because if we're going to meet a pathogen, it's probably going to be in those areas. So we tend to see a lot of these in the digestive system, respiratory, and urogenital tracts. IgE is rarely found in blood. We see this more in body fluids and skin. We're going to talk a little bit more about IgE when we get into allergies. It can actually bind to basophils and mast cells, and they can release histamine. Remember that histamine is a flare gun going off? It's kind of like a directional flare gun calling all of those immune cells over to the scene. Well, what can happen in allergies is when we have a massive release of histamine, this could possibly cause us to go into anaphylactic shock, which isn't such a good thing. So too much of histamine is not necessarily a good thing. So we'll talk a little bit more about IgE when we get into the next chapter and allergies. IgM, this is what I call the mother of all antibodies. It is the largest immunoglobulin. It's basically 5 units put together. And this is the first that is made by the fetus and is secreted into the blood during that primary response. So remember, that primary response is the first time that our immune system sees that antigen. Immune system starts making those antibodies, and IgM is going to be those first antibodies. IgD is rarely secreted, and we don't normally see it in healthy individuals. So it's the lesser known ones. The ones that we mostly talk about, IgG, IgA, IgE, and IgM. So here is a picture of all of the different types of antibodies. I'm not going to quiz you on their structure. The one that I do want to point out, which is on the bottom, is IgM. You can see why I call this the mother of all antibodies. You can see where it's got those 5 subunits together. So this is obviously the largest immunoglobulin. All right, so let's take a look at the antibodies that are secreted during our primary and secondary responses. So remember, the primary response, this is the first time that that antigen is seen. Now, this could be through natural means, getting the flu, or it could be through artificial means, getting the flu vaccine. So our B cells are going to recognize that antigen. B cells are going to divide. They're going to clone themselves, turn into those plasma cells. Some are going to differentiate into memory cells that are going to be circulating around for our long-term immunity. And we are going to get the release of antibodies. If you take a look at the graph that is in sort of that peachy color, that's our primary response. If you take a look at the antibodies that are being secreted, there's IgM and IgG. So these are going to be the first antibodies that are going to be secreted. Secondary response, thanks to those memory cells, is going to be bigger and faster. Memory cells are going to start cloning themselves. They're going to divide to form plasma cells. Plasma cells are going to rapid fire off those antibodies, and we're going to get more memory cells. So our secondary response is the blue graph, and you can see that the total amount of antibodies is much higher, and it also peaks a little bit before the primary response. So it's actually peaking about 5 days sooner than in the primary response. And this is a good thing, because if now we're seeing the flu in real time, we want our body to remember that to prevent us from getting sick. So this is why they call that secondary response the anamnestic response. Never forgetting, it's going to be bigger and it's going to be faster. And hopefully it's big enough to keep us healthy. So let's kind of go through the pathway of if we had a sneaky pathogen entering into our body, where is it actually going to meet these antibodies? So if you remember, IgA is going to be in those mucous membranes, so our respiratory, digestive tract, urogenital tract, all of those open orifices to the outside world. That's where IgA is going to be. And so IgA is going to attack those pathogens, try to surround them, try to neutralize them and keep them from getting further into our body. So try to stop them in their tracks. Now, let's say this pathogen is super sneaky and it is able to get into the tissues. The next antibody that it's going to encounter is going to be IgE. That IgE is going to release that flare gun histamine, and that histamine, that flare gun going off, is going to be bringing in all of those immune cells as well as complement. Remember, we saw complement, those 20 different proteins in the innate immune system. Now, if this pathogen is sneakier still and it gets into the lymphoid tissue without being recognized by a B cell, then macrophages are going to engulf that pathogen. And remember, those lymph nodes are going to be the conference room, the meeting place, where now those macrophages can present those gobbled up antigens that it's displaying on its cell surface, kind of like that display window, to B cells and also to T cells as well. So even if these pathogens are sneaky, hopefully our immune system can recognize them along their path. So the last thing that we will talk about, how is it that antibodies fight off microbes? So I've got some of my little drawings here, and the first one is agglutination. Agglutination means clumping. And so IgM can actually bind to the pathogens and allow them to all stick together. It's almost like glue that's going to allow them to kind of congregate and stick together. And those clumps are actually going to be easier for those phagocytes to find. So you can see my phagocyte that kind of looks like a Pac-Man, and there's a pathogen that's encoded with that IgM. They're all clumped together, and now that phagocyte can gobble them up. Opsonization is another thing that antibodies can do. Remember that term opsonize? That means that we are going to coat that pathogen. So that pathogen can be coated with the antibody. Phagocytes are going to be able to bind to those antibodies and then gobble them up. So antibodies can coat a pathogen, that opsonization. The other thing that they can do is that they can activate complement. So IgM and IgG mostly will bind to complement and activate that system. And remember, complement has to do with that inflammatory response. And I mentioned that we talked about complement in the innate system. We would also see it again in our adapted or acquired immune system. Remember, this is a whole body system, and they're all working together to keep us healthy, basically. The other way that antibodies can fight antigens is through neutralization. And this is really what I think of typically when I think of how antibodies are going to fight pathogens and antigens. They can basically coat a pathogen and block their action. So if you remember, if bacteria can bind to cells, they're going to be dangerous. Viruses are not going to be able to replicate unless they bind to a cell. Remember that term, adsorption. So with that neutralization, those antibodies coat the pathogen and basically keep it in a bubble. So if it's trapped in this bubble and it bounces into a cell, it's going to bounce right off. It's not going to be able to bind. This is typically what I think of when I think of what antibodies do to help protect us. And finally, the last thing is that IgM can directly lyse some cell membranes. So IgM can bind to bacteria and lyse them. You punch a hole through a bacteria and it's not going to be able to live. So this has to do with antibody-mediated immunity, which is really governed by our B cells. Up next, we're going to talk about the second arm of the acquired immune system, which is cell-mediated immunity, which is going to be governed by T cells.